Today, we'll explore the concept of dummy-dependent variables within qualitative response models. This sets the foundation for understanding how discrete choices are modeled in regression analysis, a crucial topic in econometrics and statistics. Let's start by understanding what a qualitative response model is. It deals with situations where the dependent variable represents a discrete choice, taking on only a limited set of values. These models are often called limited dependent variable models or discrete dependent variable models. We'll also look at the two broad categories of these models. The first category is the binomial model, which involves a choice between two alternatives. For example, deciding whether to participate in the labor force or not. The second is the multinomial model, where choices exceed two alternatives, like different occupations. It's important to know about binary variables, which have two categories and indicate whether an event occurred or a characteristic is present. Moving on, we have ordinal variables, which are categories that can be ranked. For instance, education levels ranked from primary to university. Then there are nominal variables, which represent multiple outcomes without any inherent order, such as different job types. An example of nominal variables would be occupations grouped as farming, fishing, carpentry, and government employment. The numbers assigned to these categories are arbitrary. Additionally, count variables indicate the number of times an event occurs, like years of education. All these variables are discrete valued, which means they take specific separate values. When analyzing such discrete data, standard regression models don't suffice. Instead, we use qualitative choice models, which apply when a decision maker faces a finite number of mutually exclusive and exhaustive choices. This means the person selects only one option from all possible alternatives. Focusing on binary qualitative choices, we assign the dependent variable values of 0 or 1 for convenience. For example, the choice to work or not is represented as 1 if the individual works, 0 if not. This binary setup simplifies modeling decisions with two alternatives. The independent variables, or factors, influencing this choice might include age, marital status, gender, and education. These are organized into a matrix X. The economic interpretation relies on utility maximization. An individual chooses to work if the utility from working exceeds that of not working, which depends on these factors. The probability that an individual chooses to work, given their characteristics, is expressed as a function g of those factors and parameters beta. Beta measures how changes in factors like age or education impact the likelihood of labor force participation. Conversely, the probability of not working is 1 minus this probability. We call the probability of choosing to work the response probability, and the probability of not working the non-response probability. The expected value of the dependent variable, given the individual's characteristics, equals this response probability. The challenge lies in selecting the appropriate form for the function g. There are several approaches to estimating binary response models. The four most common are the linear probability model, the logit model, the probit model, and the tobit model. Each offers a different way to handle the binary nature of the dependent variable. The linear probability model, popular in the 1960s and early 1970s, is straightforward to estimate using multiple regression. It deals with limited dependent variables that take on a limited set of values, such as binary, multinomial, or integer values. Traditionally, parametric maximum likelihood methods estimate these models. Parametric models allow us to construct likelihood functions based on assumed distributions. More modern approaches use semi-parametric methods to avoid strict distributional assumptions, but here we'll focus on the parametric approach. The linear probability model applies linear regression to a binary dependent variable. In the linear probability model, the response probability function g is defined as a linear combination of the independent variables and parameters. The regression equation expresses the binary dependent variable as a sum of these terms plus an error term. Since the dependent variable is binary, the parameters don't represent marginal changes in the usual sense, but indicate shifts between 0 and 1. Assuming the error term has zero mean, the expected value of the dependent variable equals the linear combination of independent variables and parameters. This means the probability of success is modeled as a linear function of the predictors. Similarly, the probability of failure is 1 minus this linear function. To illustrate, consider a hypothetical regression of home ownership on income. The intercept suggests the probability of owning a home at zero income, which is negative and thus treated as zero since probabilities can't be negative. The slope indicates that each unit increase in income raises the probability of home ownership by about 10%, though this linearity may not reflect reality perfectly. The parameter beta measures how the probability of success changes with a unit change in an independent variable, holding others constant. The linear probability model is easy to estimate and interpret, but its simplicity comes with drawbacks that we need to consider carefully. One drawback is that the dependent variable is discrete, while independent variables can be a mix of discrete and continuous. Also, using 0 and 1 for the dependent variable is arbitrary. Choosing other values would alter the model even if the predictors remain the same. Furthermore, the error term can only take two values, which affects its distribution. Specifically, the error term's variance depends on the predictors, leading to heteroscedasticity. This violates assumptions of constant variance and normality, making ordinary least squares estimators inefficient and standard errors biased. Consequently, statistical tests based on these estimates may be unreliable. Finally, the expected value of the error term conditional on the predictors doesn't behave as classical regression assumptions require. The binary nature of the disturbance term, being the difference between the observed binary outcome and the continuous predicted probability, leads to inconsistencies. Moreover, the linear probability model can produce predicted probabilities outside the 0 to 1 range, which is nonsensical for probabilities. Let's focus on a major issue with linear probability models, or LPMs. They often predict probabilities outside the logical range of 0 to 1, which is a fundamental problem. This means sometimes the model suggests negative probabilities or values above 1, which just doesn't make sense. Another key point is about the disturbance term, the U's. While OLS assumes these disturbances are normally distributed for inference, in LPMs, this assumption breaks down because the disturbances can only take two values, just like the dependent variable. This complicates hypothesis testing and statistical inference. Building on that, the linear nature of LPMs means that increasing a predictor by 1 unit always changes the probability by the same amount, regardless of where you start. This constant effect ignores the reality that probabilities should change more gradually near the extremes. Also, the usual measure of fit, R-squared, tends to be low and less meaningful here. Combined with issues like non-normal disturbances and heteroscedasticity, these problems make the LPM logically unattractive and statistically unreliable for modeling probabilities. Given these challenges, the LPM is generally not recommended for empirical analysis. What we really need is a probability model that respects the 0 to 1 bounds and captures the nonlinear relationship between predictors and outcome probabilities. Specifically, as the predictor increases, the probability should rise but approach 0 and 1 more slowly at the extremes, reflecting real-world behavior. This nonlinear approach ensures predictions stay sensible and improves the model's interpretability and reliability. That wraps up our discussion on why alternative models are preferred over LPMs.